Bismillahirrahmanirrahim. Chapter 43, entitled as Nuclear Physics. So in this chapter, we basically talking about the field of physics where we are concerned about the nuclear activity of a nucleus. Right. So if you see this symbol, what cross your mind? Is danger, warning about the hazard from radiation that can give us negative effects, okay, or we call it dosage, right? So actually, the beginning of the nuclear physics is when Henry Becquerel figured out radioactivity from some amount of uranium compound. Okay, so the scientists later on study about this, and Ernest Rutherford figured out that the type of the radiation or emission from nucleus of radioactive material can be categorized into three, which is alpha, beta, and gamma radiation. For your information, this is actually particle, okay, and also particle, but this one is high energy or photon or ray only. So basically, if you see this label, normally it is used in hospital, right? So when we use this kind of most of the time we use these two types of emission, okay, to treat cancer patient, right? So this emission can cause hazard, okay, damage to the cell of human being, but it also can bring goods where it can treat cancer. We are going to kill the cancer cell by using this radiation, but of course with the coordinated or controlled dose or amount of radiation introduced to the patient. Right. So before we go in details, since this is a new field for you, okay, let's take a look on the terms. Okay, where we have a nuclear physics just now, where we have a nuclear means that a bigger picture, the field of the study of the what? The nucleon, the nuclei, and the nucleus. So the most basic is actually nucleus. This is the center of an atom, where it consists of proton and neutron. Then combination of the nucleus, plural of it, we call it nuclei, right? So nuclei means that lots of nucleus. And when we talk about nucleon, sometimes there is a terms used as nucleon. When we talk about nucleon, it refers to the number of proton plus neutron within the nucleus. And just now, as I mentioned, nuclear is the field of it, the field of this study. Alright? Now, let's take a look on some properties of nuclei. Okay, atomic number, Z, is the number of the proton in nucleus, sometimes also called as charge number. And neutron number, and number of neutron in the nucleus. Mass number, A, is equivalent to Z plus N, where number of nucleons, okay, neutron plus proton in the nucleus. This is what we're talking about just now. In terms of symbol that we can refer to predictable simply, okay, it symbolized in general as X, representing the element. And we have on the top here A, okay, where it is mass number, consists of neutron and proton within the nucleus. And the Z is here, we call it atomic number, consists of number of proton. Right. So for example, ferron or iron. Okay, iron 56. Okay, it consists, mass number of it is 56 and the atomic number of it 26. So what does that mean? We have 26 proton and 56 minus 26 of neutrons within iron 56. Okay, and sometimes, okay, the Z is not mentioned. Okay, it's not mentioned. Right? It's stated only like this. Right? And if you have, for example, element carbon here, okay, carbon 12, we have carbon 13, we have carbon 11, and carbon 14. So, call it isotopes. Okay, where the Z is the same, okay, the A is different. And the most abundant is actually carbon 12. In nature, the composition of it is 98.9%. We have carbon 12 in our environment. Okay, carbon 13 only 1.1%. Carbon 11 and carbon 14 produced in lab or by cosmic ray. This is, the amount is very small and you have to produce it artificially. Okay, charge and mass. If you refer to this table, okay, listed here, different masses for each of the element, proton, neutron, electron, hydrogen atom. This is alpha particle, okay, it's helium-4 2, okay, and then we have carbon 12, okay, listed here the mass, okay, in terms of atomic mass unit, okay, because in terms of mass, the mass of the proton is way too small if you are using kilogram unit. So another unit is introduced, is atomic mass unit, or symbolized as U. Okay, for proton, for example here, for proton, in terms of U is equivalent to 1.007276 atomic mass unit. Okay. So, in terms of energy here, what is energy here? This is energy at the rest. This is rest energy equivalent. Okay, so this one, rest energy equivalent, which is figured out by Einstein. It's equivalent to mc squared, right? Because all of these elements moving at the speed of the particle, moving at the speed of lights. So the c here is the speed of lights. So mc squared. So m here is the mass of the element in kilogram, times with the c here to be exact. C is 2.99792 times 10 to the power of 8 squared. So this is the rest energy equivalent. It means that at rest, okay, proton having this amount of energy, where it is measured in mega electron volt per c squared. Okay, so what is electron volt? Okay, we've learned this in photoelectric effect. This is also a unit for energy, but when we deal with electron proton, because joule is way too big for proton, neutron, the tiny miny element here or particle here. And not to forget that elementary amount of charge. Okay, so for one proton, the elementary amount of charge is equivalent to positive 1.6 times 10 to the power of negative 19 coulomb of charge. For electron It brings or consists of negative 1.6 times 10 to the power of negative 19 coulomb of charge, okay, of electric charge within one single electron. So for 1 AMU, for 1 atomic mass unit or 1 U, the conversion factor in kilogram is 1 U equivalent to 1.660539 times 10 to the power of negative 27 kilogram. For 1 atomic mass unit or 1 U, the rest energy equivalent based on mc squared is equivalent to average m in a kilogram times with the c squared, where the c to be exact is 2.99792 times 10 to the power of 8 squared. So this is the amount of the rest energy equivalent for 1 atomic mass unit. The size and structure of nuclei. So based on Rutherford experiment, okay, it is accepted that the nucleus, okay, is considered as a spherical shape, right? Therefore, from the experiment, it is come up with the idea that the radius of the nuclei is equivalent to A times A mass number power of 1 over 3, where the A is a constant value is equivalent to 1.2 times 10 to the power of negative 15 meter. So since the order of this in meter is very small, therefore we have another unit for length, which is FM or femtometer. 1 femtometer equivalent to 1 times 10 to the power of negative 15 meter. So from here, 1.2 times 10 to the power of negative 15 meter is equivalent to 1.2 femtometer. This proportionality suggests that all nuclei have nearly the same density. When nucleon combine to form a nucleus, they combine as though they were tightly packed spheres, as visualized here. This fact has led to an analogy between the nucleus and a drop of liquid, in which density of the drop is independent of its size. Right. So example 43.1, the volume and density of a nucleus. Consider a nucleus of mass number A containing protons and neutrons, each with mass approximately equals to m. A, find an approximate expression for the mass of the nucleus. So mass of the nucleus more or less to A times m, because the A is the number of the nucleon, consisting number of proton plus neutrons, times with mass for one single neutron or proton. That is why we have this idea. B, find an expression for the volume of this nucleus in terms of A. So since we consider this as a spherical in shape, okay, so the volume of the nucleus take a place of a sphere, 4 over 3 pi r cube, which equivalent to our r itself is equivalent to A times mass number power 3. If you have to cube this part, you are going to cube this part as well. That is how the formula simplified like this. Find the numerical value for the density of this nucleus. As we know, density is equivalent to mass over volume. And the mass just now is A times m. The volume is equivalent to 4 over 3 pi A cube times A. So we can cancel out the A. right? So we are left with this. Substitute the rest of the information, the M, right, and the A. Then you will have 2.3 times 10 to the power of 17 kilogram per meter cube. So very large amount. What if the earth could be compressed until it had this density? How large would it be? So let's repeat the calculation, but now consider the earth density is equivalent to the one that we calculated in previous part. Volume equivalent to mass over rho. Coming from the equation just now, rho equivalent to mass over volume, right? So from here, we calculate the volume. It's 2.6 times 10 to the power of 7 meter cube. Okay, and we know volume also equivalent to 4/3 pi r cube, because we consider our earth almost a spherical in shape, sphere. So from here, our r is equivalent to 1.8 times 10 to the power of 2 meter. So from this, the earth with this radius is indeed a very small earth. Nuclear stability. Within the nucleus, there is a neutron and proton packed in a tiny space, okay, taking a shape of sphere, right? And the nuclear force that hold them together is a very short range force, where attractive force that acts between all nuclear particles. Okay, the protons attract each other by means of the nuclear force, and at the same time they repel each other through the Coulomb force, because they are the same charge. The nuclear force also acts between the pair of neutrons and between neutrons and protons. The nuclear force dominates the Coulomb repulsive force within the nucleus, within the short range, remember. So, stable nuclei can exist. If not, how could proton and neutrons combined within tiny sphere? So if you refer to this graph given here, okay, this is an neutron proton system, where we are observing the energy between neutron and proton within the nucleus. And here you have proton and proton system. Okay, if you refer to this shape of energy, potential energy versus the distance, the r between neutron and proton. So if you refer here, okay, it is most stable within up to 2, okay, up to 2 femtometer, because it is a kind of short range force. Nuclear force is a kind of short range force. But if you refer to this graph, there is a slightly different here, right? So the different here is due to the Coulomb repulsion in the case of the proton-proton system, because proton-proton has, both of it has positive sign in charge, so they repel each other. That is why the difference in shape of the U versus R energy for PP system or proton-proton system slightly different compared to this one. The depth of the neutron-proton potential energy well, we call it, this is energy well, is about 40 to 50, more or less, MeV, mega electron volt. And there is a strong repulsive component that prevents the nucleons from approaching much closer than 0.4 femtometer. Okay, there is a theory saying that if it is allowed, then the proton will collapse into neutron. Then there will be no nucleus exist because they collapse, right? So that does not happen. That is why within this kind of energy well, right? The nuclear force is independent of charge. Therefore, the main difference between neutron-proton system and proton-proton system interaction is the proton-proton potential energy consists of superposition of nuclear force and also Coulomb force or interaction, as shown in this figure. At distance less than 2 femtometers, both proton-proton and neutron-proton interaction or energy are nearly identical. So if you refer to the shape of the well, it's nearly identical. But for distance more than 2 femtometer, the PP potential has a positive energy barrier with a maximum at 4 femtometer. The existence of the nuclear force results in approximately 270 stable nuclei. Hundreds of other nuclei have been observed, but they are unstable, meaning that they decay spontaneously by the process really called radioactivity. Okay, for this graph, a plot of number of neutrons versus atomic number. Okay, if we see here, okay, we have dash line here where the N is equivalent to Z, and the stable nuclei lie in a narrow band called the line of the stability here. The stable nuclei are represented by the black dot which lie in narrow range here. Okay, if you notice here, heavy nuclei, the number of neutron exceed the number of proton. The number of neutron bigger than number of the proton. Above Z equivalent to 20, the line of the stability deviates upward from the line representing N equivalent to Z. This deviation can be understood by recognizing that as the number of proton increase, the strength of the Coulomb force also going to be increased, which tend to break the nucleus apart because it's a kind of repulsive force. As a result, more neutrons are needed to keep the nucleus stable because neutrons experience only the attractive nuclear force, which is short-range force. Eventually, the repulsive Coulomb force between protons cannot be compensated by the addition of more neutron anymore. Alright, this point occurs at Z equivalent to 83. Right? Meaning that elements that contain more than 83 protons do not have stable nuclei. It's going to decay. Right? Or a process, what we call it, radioactivity going to take place. Talking about the stability just now, it also can be understood by referring to the nuclear binding energy between the nucleons. So what is binding energy? It's energy that must be added to nucleus to break it apart into its components or its nucleons, right? So this is the energy to break, okay, the nucleus into its part or components. So, based on the concept or come up with the idea from the Einstein, okay, energy involved in binding energy, okay, is equivalent to originally mc squared. So if we're talking about binding energy, is equivalent to how much changes of the mass after the nucleus breaks into its components compared to initially when they are combined as a nucleus times with a c squared. It means that mass in terms of components minus mass as nucleus. Okay, this is your delta M times with a c squared. So in terms of components, you will have how many Z times mass of proton plus, okay, N times mass for one neutron. Okay, this is the mass of the component minus mass of the nucleus as it is initially X, where it has A and Z. Okay, then whole bulk of this is your delta M, times with the c squared. The c squared in terms of equivalent is 931.494 MeV. This is already in conversion factor, okay? MeV over atomic mass unit. So this is what written here, right? The whole bulk in the bracket here is the change in mass, right? Times with the conversion factor in terms of c squared, where it is MeV over U. So this is on how to calculate binding energy. What is binding energy again? Energy that must be added or needed to break the nucleus into its components. Okay, now let's take a look on the graph of the nuclear binding energy. So just now we've already taken a look on the equation for the nuclear binding energy is equivalent to this. Alright, so now if we plot the graph of binding energy per nucleon over or versus mass number. Why is it must be binding energy per nucleon? It's because to compare, okay, whether a nucleus is stable or not, we refer to the binding energy, because in simple, binding energy is the amount of energy needed to break the nucleus into its component, to the nucleon. So if we, for example, compare oxygen 16, right? For oxygen, the binding energy needed to break the nucleus into its components, okay, where two neutrons and proton, about 128 MeV. If we compare to the one that famous for nuclear reactor or atomic bomb is uranium-235. The nuclear binding energy, okay, for uranium-235 is 1786 MeV. So if we refer to this, it seems like, okay, uranium-235 having a bigger amount of binding energy. It means that it more stable, because to break into from one nucleus of uranium into 235 components, we need 1786 MeV. To break oxygen into 16 components, we need only 128 MeV. So it seems like uranium is even stable compared to oxygen. But this is not true actually, because the nuclear energy is short range energy. Okay. When you add up more particles, more components, more neutrons into the nucleus, okay, the size of the nucleus become big, bigger and bigger. So the short range force is no longer adding up. Okay, it become a constant. Okay, so let's take a look in detail for EB over A, right? If we put it EB over BA for oxygen, it's about 8 MeV. This is what we're talking about, the graph here. This is EB over A, nuclear binding energy per nucleon. Okay, this is EB over A. So now, for uranium, right, the EB over A will be about 7.6 MeV. It means that oxygen is even stable, more stable compared to the uranium-235. That is why uranium is more fissionable in nuclear reactor. Alright, so if we refer to this graph, we have a lighter element, and we have ferron 56 iron and nickel, okay, 62. And then after that we have a bigger amount of nuclei within the element. And as we know, uranium and radium is most unstable. So in terms of graph, the line of the graph, yeah, we can see that, okay, almost, okay, this is the highest amount binding energy per nucleon, the highest amount. So within the 10 area here, where we have ferron or iron and nickel here, having the biggest amount, almost the largest amount of the binding energy per nucleon. It means that nickel here is the most stable, right? The most stable element. Alright. So, how to reach by nature, how to reach stability, how to become more stable for the element at this region and this region. Okay, so for the region here, for the lighter element here, if we break it into a part, okay, or we call it in nuclear reaction, fission, okay, it become less in mass number. So of course it's going to skew into this. So it becomes less amount of binding energy per nucleon, less stable. So that is not favorable by nature. So what should be done, or what's going to happen by nature, okay, for the lighter element, they're going to fuse, they're going to combine. So let's say this element and this element combined, okay, they will get higher in terms of mass number. Let's say element here combine with the element here, right, and then become another element here. So the combined element, the product of the combination between these two elements will be in a higher stability, because the amount of nuclear binding energy per nucleon is bigger compared to the element number 1 and 2 that combine become number 3. So in nuclear reaction, we call it as fusion. For uranium, for example, the element here, okay, to reach stability by nature, is going to break into 2 components, right? So from 1, it becomes component 2, element 2 and element 3. So both of the product, element 2 and element 3, will be higher in stability because the binding energy is bigger compared to the original or element 1. Okay, for this process, in nuclear reaction, we call it fission. Okay, where the original element is break into another elements. Okay, for this one, 2 elements combine to create third element where it has higher binding energy per nucleons, so become more stable. This is what is happening in the stars and the sun. Alright, this is a common that we've done in our nuclear reactor to produce some amount of energy to use up as electricity source and so on. So this is an explanation or how to read, okay, or how to use the information of binding energy per nucleon. Okay, the bigger the amount the binding energy per nucleon, the more stable the element is. Now let's take a look on few questions as your examples. So this is question number 7 from your textbook, page 1220. Part A, calculate the difference in binding energy per nucleon for the nuclei of natrium and magnesium. B, how do you account for the difference? So let's solve part A firstly. To calculate binding energy, we need to use this formula. Alright, so for natrium, firstly, we are going to use 11, the Z is 11. So 11 times with the mass of hydrogen. Why is it hydrogen? Because within this, we already have proton plus electron. Okay, so the mass of hydrogen is equivalent to the total mass of the proton plus electron. That is why we use mass of hydrogen times with the Z plus we have 12 neutron. Okay, so times with the mass of the neutron, and then minus with the mass of the natrium nuclei, okay, as a whole, as a bulk. Okay, then the difference in mass here times with the conversion factor, okay, MeV over U. So we will have 186.565 MeV. This is binding energy. If we're talking about binding energy per nucleon, since we need to do comparison, so divided by A, divided by 23. So this is the binding energy for natrium per nucleon. Right. Now let's proceed for magnesium. Right. So again, we are going to repeat the same, okay, calculation. 12 times with the mass of hydrogen plus 11, okay, of neutron times with the mass of the neutron minus mass of the magnesium as a bulk, as a nuclei, times with the conversion factor. So you will have 181.726 MeV. This is binding energy. If we want to have a comparison again, we have to divide it by number of the nucleon. So we have 7.90 MeV. So now let's compare in answering part B, okay? So we need to do the comparison, the difference, okay? We need to have the difference, okay? So binding energy per nucleon of the natrium minus binding energy for the magnesium, okay, per nucleon as well, you will have 0.210 MeV. What does that mean by this final answer here? The binding energy per nucleon is greater for the natrium by this amount. What does that mean? There is less proton repulsion in natrium. Okay, so it is the more stable the nucleus is. Okay, now question number 26, page 1221. Natural gold has only one isotope, which is aurum. Okay, if natural gold is irradiated by a flux of slow neutrons, okay, electrons are emitted. Write the reaction equation. B, calculate the maximum energy of the emitted electrons. Alright, so the reaction, aurum is bombarded with neutron, producing excited aurum, and finally going to release mercury plus one electron or negatron accompanied with antineutrino for the conservation of energy. Right? You have to make sure all the Z are balanced. Okay? All the A as well must be conserved or balanced. Okay, B. Calculate the maximum energy of the emitted electron. So let's consider adding 79 electrons. Okay, so what will happen? Okay, the equation just now going to be aurum atom bombarded with neutron producing mercury atom plus antineutrino plus Q. Okay, so the Q here, okay, must be equivalent to delta M C squared. Right. So what is the delta M? This is the mass of the aurum as a whole, as a bulk, okay, the nuclei, plus mass of the neutron, okay, as we bombard the aurum with the neutron, okay, minus mass of the product, which is the mercury as a bulk, times with the conversion factor. So you will get the answer 7.89 MeV. Right. Now let's move to question number 27, page 1221 as well. Identify the unknown nuclides and particles X and X prime in the nuclear reaction of. All the time, the idea must be the A and the Z must be conserved. So let me rewrite the equation in part A. So we have X plus helium 42 producing magnesium 2412 plus 10 of neutron. X here we have A, we have Z. So for A, right, plus 4 is equivalent to 24 plus 1. So to have A only is equivalent to 24 plus 1 minus 4. That is how you get the A is 21. Right. For the Z, Z plus 2 equivalent to 12 plus 0. So the Z is equivalent to 12 minus 2. You will get 10. That is how, okay, we know that the amount of the A for our X element is 21 and the amount of Z for the X element is 10. If you refer this to periodic table, you will get this is actually neon. Right. So we are going to repeat the same thing with the equation B. So now you have uranium. You have 235 plus 1 equivalent to 90 plus A plus 2 times 1. Okay, so from here you will get 235 plus 1 minus 90 minus 2 is equivalent to A. Right? Now, which give you A equivalent to 144. Okay, the first one. Right? The second. Okay, second part. For Z. Okay, you have the 92 plus 0 equivalent to 38 plus Z minus 2 times 0 will give you Z is equivalent to 92 minus 38, which equivalent to 54. So with this amount of A and Z, right, refer to periodic table and you will figure out this or not. Okay. So now for C, again, we are going to repeat the same method, okay, whereby, okay, we take a look on the Z firstly. right? So if you refer the Z, it's 2 minus 1 is equivalent to positive 1. So if this one is positive, okay, it must be positron. Okay, for the A, it's 2 minus 2 equivalent to 0, right? It's conserved. So it means that the ejection is positron. As it is ejected, it is accompanied by neutrino.